When you open a browser and type a web address, it feels instant. But behind that click lies
What you see, buttons, images, text, belongs to the surface layer. This is the front end.
when you click a link, your browser sends a request, a structured packet of data, asking a server somewhere in the world to deliver content back.
Servers are the powerful machines that store and deliver content. Every image, video, or message lives somewhere on one of these machines. Your browser translates raw code into visual experience. It reads HTML like a script, executes JavaScript, and styles everything through CSS.
To you, a web page looks flat, but in reality, it's a symphony of interconnected layers.
Once you hit enter, your request leaves your device and travels across the internet's physical backbone, FUTed, the network. Data is broken into packets, small fragments of information that travel independently before being reassembled at their destination. Each packet takes the most efficient route based on routing algorithms, sometimes across continents, before rejoining the others. Finally, all packets arrive at your device. The browser reassembles them to reconstruct the full web page you requested knowing, almost instantly. Every time you enter a web address, your computer first consults the domain name system, the phone book of the internet that turns names into numbers. Every device online has a unique address, an IP, defining its location in the global network. Without it, data would never know where to go.
The old IPv4 system offered just over 4 billion addresses. Today, IP
Routers act like digital traffic officers, directing packets from one network to another, ensuring they reach their destination safely. Every connection happens through ports, numbered channels that define specific kinds of communication: web, email, streaming, and more.
The Hypertext Transfer Protocol defines how browsers and servers talk. It's the polite conversation that delivers every web page. The S in HTTPS means security, encryption that protects your data as it moves between you and the server.
Secure connections begin with a digital handshake, SSL or TLS, where both sides verify identity and agree on how to encrypt data.
Each data packet carries not only information, but also a header, like an envelope jounce, telling routers where it's from and where it's going.
Every packet has a lifespan, called time to live. If it can't reach its target in time, it's discarded to keep the network clean.
A ping sends a tiny packet out and waits for an echo, a simple way to measure distance and speed between 2 points.
Traceroute reveals every stop a packet maze on its path. Each hop tells part of the internet's hidden geography.
Firewalls monitor and filter packets load, deciding what's safe to enter or leave. They're the border control of the digital world. Proxy servers act as middlemen, fetching content on your behalf, adding privacy or caching speed in between.
Together, these protocols, DNSP, HTTP, and encryption WAN.
Beneath every digital click lies a physical world of cables, switches, and power, the true machinery of the internet.
Every connection starts at a network card, translating computer data into electrical or optical signals.
Switches manage traffic inside local networks, directing packets between nearby devices instantly.
Your home router connects to an internet service provider, the gateway that links private space to the global net.
Massive data highways called backbones connect continents, operated by Tier 1 providers handling global traffic.
Thousands of kilometers of fiber optic cables lie across ocean floors, carrying nearly all international data.
signal amplifiers called repeaters boost light every few dozen kilometers to keep data strong across oceans.
At landfall, data flows into colossal data centers, the silent warehouses of the internet.
Each server farm consumes megawatts of power. Cooling systems maintain stability and prevent meltdown.
Load balancers distribute requests across many servers to keep response fast and reliable.
To survive failures, the internet is built with redundancy. Multiple routes ensure continuity when one fails.
Routers communicate using protocols like BGP, exchanging paths and deciding the best way to send data.
The internet is divided into autonomous systems, with networks run by organizations that exchange routes with others.
At peering points, major networks interconnect directly, improving speed and reducing cost.
Billions of packets traverse this physical backbone every second. A living organism pulsing with information. The transport layer controls how data travels between 2 points, ensuring everything arrives complete and in order.
TCP breaks messages into packets, numbers them, and reassembles them precisely at the destination.
Every TCP session starts with a three-way handshake. SYN, SYN.
Each packet carries a sequence number, and every received packet sends back an acknowledgement relay. A constant dialogue in
Some data, like streaming or gaming, uses UDP, sending packets without checks to gain speed over reliability.
Sockets bind IP addresses to specific ports, creating unique channels for communication between devices.
TCP's flow control adjusts transmission rate based on how fast the receiver can process data.
When the network becomes crowded, congestion control reduces traffic, preventing collapse and maintaining balance.
Checksums in each packet help detect corruption, and if something changes, it's discarded and resent instantly.
If data is lost, TCP retransmits automatically far, ensuring reliability even in unstable conditions.
Large messages are segmented into packets, then reassembled perfectly on arrival, like digital puzzle pieces.
Encryption transforms plain text into ciphered code, HEIN, unreadable without the correct key.
On the other end, the receiver decrypts it, restoring clarity while ensuring authenticity and integrity.
Sessions maintain context across multiple exchanges, like remembering your login while you browse.
Layer by layer, the transport system carries, verifies, and protects the flow of information we depend on every second.
Beneath the websites we browse lies the deep web, massive, invisible networks powering the modern internet.
The deep web includes databases, internal systems, and password-protected areas not indexed by search engines.
APIs act as controlled gateways, allowing systems to exchange information without exposing their core.
Search engines index the surface, but deep queries tap directly into structured databases portal, retrieving data live.
Relational databases organize information into tables, linked by keys, forming the structured backbone of web data.
NoSQL databases trade strict structure for flexibility tools, perfect for massive, unstructured information flows. Vast data centers house the deep web's engines, endless racks processing billions of requests per second.
Caching stores recent data closer to users' retina, reducing latency and powering faster access to dynamic content. Corporations run private intranets, internal webs protected by firewalls and access controls.
Firewalls inspect and filter data, defining what can enter or leave a protected network. VPNs wrap your data in encryption, creating a secure tunnel between you and the destination.
More than 90% of all online content resides in the deep web, unseen but essential.
Even stored data remains encrypted, protecting information at rest from unauthorized access.
APIs, databases, and encryption form bridges frame, quietly connecting the visible web to the vast systems below.
Beyond the deep web lies an even more hidden layer, the dark web, accessed through encrypted routing systems.
TOR, short for the onion router, hides users' identity by wrapping traffic in multiple layers of encryption.
Every Tor packet passes through several relays. Each decrypts one layer, never knowing the full path.
Relay nodes keep users anonymous, with exit points connect to the public web torrent, where encryption ends.
Anonymous marketplaces operate here, using cryptocurrency and hidden addresses instead of domains.
Cryptocurrencies allow value transfer without identity, blending finance and cryptography within this network.
Encryption secures both access and communication, live, from message content to routing metadata.
Hidden messaging protocols route traffic through encrypted paths, concealing both sender and receiver. It was designed for privacy and free information exchange, though often misunderstood by the public.
Like any technology, anonymity can be exploited, Braug, leading to criminal activities and digital threats.
Tracking cybercrime through encrypted layers requires international cooperation and advanced forensics. Society continues to balance privacy rights against the need for digital safety and accountability.
New privacy-focused protocols aim to protect users without enabling harm, the next evolution of secure networking.
The dark web remains the invisible backbone of encrypted communication. The internet isn't single machine attuned. It's a living structure of millions of systems communicating in harmony.
Data flows like oxygen through every digital vein, powering businesses, governments, and human creativity. We depend on this invisible infrastructure, yet few truly see how it connects every message, image, and idea.
The next era of the internet will blend artificial intelligence, quantum security, and seamless global communication. Every packet, every signal is part of something larger, the shared digital consciousness we call the internet.